Date on another. Okay, listen. Today we are going to discuss about the force between the current carrying conductor. So you can consider two straight conductor P and Q. Okay, that's how the flow of current I1 and I2. If the current is in the same direction, if a considered conductor that is a P and Q, it is separated by the small distance D. Okay, if the current in the conductor I1 as well as I2 in the both are in the same direction, the resultant value is the force of attraction. Similarly, if the current in the opposite direction, the resultant force it will be getting reflected. So if you are finding the magnetic flux density in the conductor P, it's due to the current flow I1. So the B it should be equal to mu naught into I1 divided by 2 pi D. Okay, that is the formula. If you are finding the force due to the conductor Q, F equal to B into IL, sorry, the B into I2 into L. The L is the length of the conductor. So the resultant force, it should be equal to mu naught into I1 and I2 L divided by 2 pi D. That is the whether it is the resultant force it is getting attracted or repelled. The resultant force equation is like that. If the current in the opposite direction, here itself the value is getting subtracted. So the resultant force it may getting varied depends on the current direction. Okay, that is the force between the current carrying conductor or two parallel conductor. Okay, so the another topic, the magnetic torque and magnetic moment. You can consider the rectangle loop of the conductor. It's have the length L and the breadth B. If you are faced with the rectangular loop conductor in the magnetic field, so the magnetic field that is the flux density direction. So here also the conductor has been induced some EMF. So here also now the pole has been formed. So due to that, it will be trying to rotate in the field. That is the rotating magnetic field. So the rotational force we can calculate from the as usual formula, that is the F equal to BIL sin theta. That is the force in the current carrying conductor that already we derived. So the F equal to BIL sin theta. So due to that force, the rectangle magnetic loop, due to that force, the rectangle coil it is trying to move. So that rotate, it is trying to move. Finally, it has been rotated. So that is the because of the torque, the developed torque. That we can call it as the magnetic torque. That we can found through this expression. You are consider the two different side. That is why the 2 into the torque in both the side. That is the torque in both the side. While you are finding the torque, that is the movement, that is the force into distance. So the force formula we know, that is the BIL sin theta. Then distance here, if you are consider the rectangle coil, it is the mid of the axis, it is trying to rotate. So the breadth, total breadth is B. So the mid axis, it's have the breadth, that is the distance, that is the P by 2. So 2 into BIL sin theta, that is the force formula. The distance was B by 2. So the 2 and 2 it is getting cancelled. The resultant value BIL into B. So the small b and L, that is the breadth and the length, we can replace in the area, because we know that is the formula for the area, length into breadth. So the L is the length, B is the breadth. So we can replace, that is the area, then current, then magnetic flux density, then the formula from the relationship, the sin theta will come. That is the sin theta is nothing but that is the axis of rotation. Okay, due to the movement. So the conductor it is trying to move, so that is trying to rotate. So the rotational force is called the torque. The axis of movement, that is the area, that is the I into A, that is the magnetic moment. This is for the magnetic torque and the magnetic moment. Okay. If you have doubt, you may ask.